Greetings, I'm Kallol Chakrabarty, a postdoctoral fellow at University of Alabama at Birmingham. I completed my PhD here at UB in 2023. My PhD mentor was Dr. Shane Aaron Catles. Now I'm working with Dr. Yogesh Bora in the Department of Physics at UB. Here is the outline of the presentation. First, I will describe the specific research goal of this project. Then I'll describe what is Superhard material and why we are interested in the CNOB material. CNOB materials mean carbon, nitrogen, oxygen, and boron materials. Then I will show some research methodology and discuss the result and conclusion of this whole project. To begin with, we have three research goals in mind. Goal one was to identify the electronically excited critical growth species leading to superhard snob materials in microplasma chemical vapor deposition system. And our next goal was to, if we can control the growth species of the superhard snob material by changing the microwave power, chamber pressure, and the gas flow rate. And our ultimate goal was to synthesize the superhard material in the SNOB system. And in this regard, we have synthesized 5 different superhard material. But for the sake of the time, today I'll focus on the boron-rich boron carbide and boron-rich boron nitride is called BC10N material. By definition, a superhard material is a material with a hardness value of exceeding 40 gigapascal, and they are virtually incompressible solid with high bond covalency. And the primary aim of the superhard material is to develop a novel material with enhanced compressive performance, such as hardness, fracture toughness, and thermal stability. And for this presentation, I'll focus only on the hardness aspect of the superhard material. There are different applications of the superhard material. They can be used as a biomedical implant, as a hip and knee joint. Then it could also be used as a cutting tools. They are also being used in body, vehicle, and ballistic armor. They can also be used as an abrasive component, wear resistant and protective coating. And recently, they are also being used in aerospace as well. Here is the superhard market trend. In 2017, the revenue from the superhard market was 4.41 billion, and in 2025, it is supposed to be more than 6.5 billion. And alone from the diamond industry, it was half of the revenue. It was around 2.5 billion, and it is predicted that with the coming year, it will be more than 10 billion in next 10 years. Now I will describe why we are interested in the SNOB materials such as carbon, nitrogen, oxygen, and boron material. So they form strong covalent bond and comprise some of the hardest known material. And they can also form very short bond length and are inclined to form directional covalent bond, making the structure they form difficult to compress or distort. And the SNOB system is relatively unexplored for low pressure, low temperature synthesis. And the structural range of potential superhard structure is being reported or theorized is expanding. As we know, the diamond is the superhard material and it has a hardness around 100 GPa, but it has some limitation because it is prone to oxidation around at 700 degrees centigrade and also limited by high cost. And we cannot use diamond in application where temperature reaches to around 1500 degrees centigrade. Our second hardest superhard material is cubic boron nitride, but its hardness is around 60 GPa and have high thermal conductivity and external wear resistance and good chemical inertness. Boron-rich boron carbide, another material from the SNOB system, have high melting point, high thermal stability, and high mechanical strength and high neutron absorption capability. And the ternary BCN material also have some similar properties as well as superhard boron nitride and boron carbide. Now I will show the research methodology I have used. For synthesis of my superhard material, I have used the microwave plasma chemical vapor deposition system. And I have used silicon as a substrate, and I have substrated my coating on the silicon substrate. Here you can see this portion is called the bell jar, and in the inside of the bell jar, plasma is ignited. With the microwave source, we can ignite the plasma in the bell jar with different gases. And as you can see, we also have an adjustable stage here, so we can adjust the substrate height in the plasma so that we can get different temperature of the substrate. And we can measure the temperature of the substrate or coating by this IR infrared pyrometer, and we can also measure the optical emission spectroscopy of this plasma by the optical fiber. So this is the chamber what I have used to synthesize different material using the chemical vapor deposition. What is plasma enhanceability? So in the previous webinar, you have already know what is plasma is, and today I'll focus what is plasma enhanced chemical vapor deposition. So the chemical vapor deposition process that uses the plasma is called plasma enhanced CVD. And in the microplasma CVD, plasma is created either by the RF electromagnetic waves or the microwave. In our case, it was microwave. And as you can see, microwave is used to dissociate the gas molecule in vacuum and creates plasma. This energy in our case is microwave, and it's used to break down the gas molecule, and we'll get some fragmentation. We get the ionization in the plasma and the excited particle. So here our plasma is created in our plasma enhanced CVD chamber. Here is the snapshot of the CNOB research. We successfully identify the critical growth species from our plasma, and we are able to control our growth species by changing some different parameters such as microwave power, chamber pressure, gas flow rate, and substrate temperature. And we are able to synthesize superhard material which we wanted to synthesize. Those superhard material was B50C to BCTNN. Although we are not able to synthesize the superhard boron-rich boron nitride, but we get some insights from this project, and we are able to synthesize stable hexagonal boron nitride. Then we introduce a DC biasing in our microplasma CVD chamber, and we can get cubic boron nitride and outside boron nitride from this chamber. And next, we have introduced the argon ion in our gas, and we can convert 75% boron nitride to cubic boron nitride. Now I will show you some of the result of my projects. First of all, we measured the optical emission spectroscopy to find out what are the electronically excited growth species in the plasma. Here is the snapshot of the ways when different gases are present in the plasma. So the diboron, hydrogen, nitrogen, and methane was present in the plasma. And as you can see, we can get the atomic boron, BH, nitrogen, CN, and C2, and hydrogen pink in the optical emission spectroscopy. So our next goal was if we can tune or modulate those atomic boron or C2 or CN peak in the plasma so that we can synthesize our desired bases in our microwave plasma CVD chamber. Here is the goal 2, where we were able to modulate or tune the atomic boron and other growth species by changing the pressure and power of the plasma. The top panel where we keep our power constant and change the pressure. And as you can see, when our power was constant and we are changing the pressure, with increasing pressure, the atomic boron peak intensity decreases. And the same thing happen also for the pH peak intensity. When we increase the pressure, the pH peak intensity also decreases. Now, in the bottom panel, we keep our pressure constant and increase the power. As you can see, when we increasing the power, our atomic boron peak intensity increases, as well as when we increase our power, the pH peak intensity also increases. Next, we focus on the C2 peak because it is a very important growth basis for carbon-rich BCN deposition. And as you can see, when we keep our power constant and increase the pressure, the C2 peak intensity increases and saturates at some point. And when we keep our pressure constant and increase the power, our C2 peak intensity also increases. Here we learn some different thing from our optical emission spectroscopy. The first thing is that the extent of dissociation of the diboron and the methane is higher when we are giving more power. As you can know, when we introduce more power, the more gas molecule will be breakdown and will get more intensity on the C2 and B2 and the BH peak. And as you know, as the chamber pressure increases, the plasma density also increases, leading to the more collision. And due to this collision, we are getting more C2 peak in the plasma. And the collision can also result in the recombination process as well. The higher plasma density can favor the formation of larger boron-containing cluster or particles rather than the individual atoms, such as atomic boron or pH. For this reason, when we increase the pressure, the atomic boron peak intensity decreases. Maybe we are forming a larger boron particle, but optical emission spectroscopy can only detect the excited species, so we are not being able to see it in the plasma. Now I will show you some of the result how we have synthesized the boron-rich boron carbide. Here is the SEM figure of our synthesized boron-rich boron carbide. As you can see, this moly screw is our sample holder, and we have synthesized two different boron-rich boron carbide. One sample was sitting in the flat screw, and other sample was sitting in a sample holder with the insert. And more interestingly, as you can see, when the substrates were sitting on a flat screw, we can see some amorphous nature. And when the substrate was sitting in a screw with the insert, we can see a highly crystalline structure. So it was more interesting result because by changing only the stage design, we can control the degree of crystallinity of our synthesized boron-rich boron carbide. So how do you know it is boron-rich boron carbide? So next, we did the X-ray photoelectron spectroscopy, and according to the XPS, you can see our boron atomic percentage is 81.1% and carbon is 8.7%. So that we can know it's this boron-rich boron carbide. Next, we did the high resolution XPS to confirm if we have some boron carbide peak in the spectra. And as you can see, we are seeing the BC peak in the high resolution B1S, and you can see the CV and CC peak as well in the high resolution C1S peak. So we can definitely say that our boron is bonded to the carbon according to the high resolution XPS. So the first figure was for the BC1. Now here the same thing happened for the BC2 coating, which is the highly crystalline. So as you can see, this is the boron-rich material, and we have carbon of around 12.6%, and it also bonded to the carbon as a BC bond, as you can confirm from the high-res B1S and high-res C1S. Next, we did the X-ray diffraction of our two different coatings. As I mentioned you before, our sample which was synthesized at flat sample holder has amorphous nature. And according to the XRD as well, you can see some big hump in the XRD pattern. And the other figure which suggests that this is very highly crystalline, you can see that those PC2 sample has high peak, crystalline peak and very sharp peak, which suggests that this sample is crystalline sample. Although, as you can see closely, the peak position of both BC1 and BC2 is same, although the BC2 has a bigger peak, but they are in the same position. So we can see that this sample is one kind of amorphous B50C2 type sample. This work was collaboratively done with our theoretical collaborator, Dr. Chance. They also predicted this sample B50C2, and this is the predicted unit cell of the B50C2 sample. And the right panel is the X-ray diffraction pattern. The red curve is the experimental pattern. The blue curve is the theoretical pattern. And as you can see, they are matches very well the experiment and the theory. So we can definitely say that our synthesized coating is B52C2 type coating. As you know, our main goal was to synthesize a super hard material. So we definitely need to check if our material is hard or not. That's why we did the nano indentation. And according to the nano indentation, the hardness of our material was, mean hardness of our material was 34 gigapascal. And there you can see so many indents was above than the 40 gigapascal super hard mark. And in the left panel, we have plotted the load versus displacement curve. So this is the loading curve when indenter was hitting the sample, and it is the unloading curve. And from the loading and unloading curve, we can see that the most of the deformation is elastic deformation, and the only 25 or 30% is plastically deformed. That's why we also know that this material is super hard. And in the particular indent has a hardness of around 64 GPa. So it is above than the 40 GPa, and we can definitely say that this indent suggests that this material is super hard material. This is the summary from the B50C2 work. The copious amount of atomic boron and BH in our plasma were beneficial under some growth condition to synthesize the novel superhard boron-rich B50C2. And low temperature pressure synthesis of the novel B50C2 reported for the first time in the literature from our group. And the control of the coordinate degree of crystallinity was also achieved by simply manipulating the sample stage design. Here are the three other goals what I have done in the CNOB system. One was boron-rich boron nitride, and we are successful in this project, and we was not able to synthesize the boron-rich boron nitride, but we get some insight and synthesize stable hexagonal boron nitride when we published the paper. And the next project was bias-enhanced BN deposition. We also successfully synthesized the Woodside boron nitride. And the next goal was effect of argon ion in the bias-enhanced BS deposition. And this project was also successful, and then we successfully published paper from this project as well. For the sake of the time, I'll not describe in details. Now I'll go to the next project, what we have done. The next one was synthesis of theoretically predicted novel superhard ternary BC10N material. So Dr. Chen group have predicted the novel superhard BC10N material, and why it is important to synthesize the BC10N material. As you know, from the theoretical prediction, you can see the BC10N has a hardness around 87 GPa, which is comparable to diamond. And at present, there is no superhard material with the high hardness and chemical inertness, because as you know, diamond oxidize around at 700 or 800 degrees centigrade. But for some different application, we need to go beyond 2000 degrees centigrade, such as in extreme condition. So we need to find a superhard material which is chemically inert. That's why we are motivated to synthesize this PC10N material, because it can resist the oxidation until 2000 degrees centigrade and has comparable hardness with the diamond. So our next goal was to find the optimum condition to synthesize the superhard material. We did it with the optical emission spectroscopy. As I presented you before, when we increase the power and pressure, the C2 peak intensity increases. The C2 peak intensity is very important to synthesize the BC10N material, because the BC10N material is carbon-rich material. So we need to get more C2 in the plasma so that it can be deposited in our substrate. After deposition of the BCN material, we did the X-ray photoelectron spectroscopy to get the atomic percentage of the boron, carbon, and nitrogen. As you can see, according to the survey spectra, the atomic percentage of carbon is 82%, and the boron and nitrogen is 9.5 and 8.5%. The stoichiometry is BC10N is if you need more carbon and 1-to-1 ratio of boron and nitrogen. And according to our survey spectra, the boron to nitrogen ratio is almost 1. And the carbon to boron and carbon to nitrogen ratio is 10-to-1. So it is closely matches with the stoichiometry of the BC10N. So our next goal was, is the boron and carbon is bonded itself so that we are getting the ternary BCN material. And according to the high-res spectra of C1s, we can see the CB, CC, and CN bonding in the high-res C1s. Same thing for the high-res B1s as well. We are getting the BC, BN, and most importantly, the BNC bond in the high-res B1s, which is more important. Next, our plan was to do the FTIR to see what is present in the coating. And according to the FTIR as well, we are getting the CC bonding, BN bonding, BNC bonding, CN, BC, and the BNC bonding in our synthesized coating. So it also suggests that our coating is ternary coating because we are getting the BNC coating over there. And our sample is carbon rich boron carbon nitride. So our the CC peak intensity was highest in here. Next, we did the Raman spectroscopy to see how boron is bonded to our carbon. So our diamond peak here is shifted toward the lower wave number, which suggests that the phonon is softened and we have some boron doping in our lattice. And as you can see, this is the typical spectra for boron doping. We are having peak around at 450 and 1200. So it confirms our synthesized coating is doped in boron. And we also did the photoluminescence spectra as well. And according to the photoluminescence, we also have the nitrogen center. So in our lattice, we have both the boron and nitrogen doping. So this is the BNC coating. Then we did the extra diffraction of our synthesized coating, and it matches well with theoretically predicted XRD pattern by Dr. Chan's group. As you can see, when we did the read build refinement, it confirms that our coating has around 82% of BC10N and 18% of BC2N as well. Now, if we closely look at our highest peak position, which is around 44, the green one is the BC10N and the blue one is BC2N. So as you can see, it is matches very well with the BC10N peak. So our synthesized coating in BC10N, here is another confirmation. Our main goal was to synthesize a superhard BC10N, which will be comparable to diamond and which has the better chemical inertness. So our next goal was to check whether it is superhard or not. So we did the nano indentation measurement. And according to the nano indentation, the mean hardness was 63 GPa. So it is way higher than the superhard threshold of 40 GPa. So our sample is superhard material. And as you can see, uh, among most of the data point is above the 60 GPa landmark, and one data point was as high as at 90 GPa. And when we measured the load displacement curve, as you can see, when indenter was indenting the surface, this is the loading curve, and this is the unloading curve. From the loading and unloading curve, we can definitely say that most of our deformation is only the elastic deformation, and only the 20% is the plastic deformation. That also confirm our sample is superhard material. Now the conclusion from this BC10N project, XPS and FTA confirm we have BC, CN, BN, and the BNC bonding in the synthesized coating. And XPS survey spectra also showed that the surface is composed of 82% of carbon, 9.5% of boron, and 8.5% of nitrogen, which is closely matched to the stoichiometry of the BC10. The Raman measurement has showed boron doping peaks. Diamond peak also shifted towards the lower wave number, and the result indicate the phonon bands are softened with the increasing the boron and nitrogen content, and photoluminescence also confirmed the nitrogen center in our synthesis coding. And we also did the read build refinement for the experimental extra pattern, and which is a combination of 82% of BC2N, BC10N, and only 18% of BC2N. And nano indentation hardness measurement of the synthesis coating in superhard regime with the mean hardness of 63 GPa, and the highest data point is as hard as 118 GPa. So this is the good agreement between the theory and the experiment, and we are able to publish this manuscript in the diamond related material. So what Dr. Chen predicted, the BC10N material, theoretically we have synthesized in and published as a paper in the diamond and related materials. So we can say the experiment agrees with the theoretical predictions. Now I will describe the overall summary of this project. Optical emission spectroscopy was successfully used to characterize the excited species of the plasma, and the control of the excited species was achieved by tuning the microwave power and chamber pressure. Excited species and the free radical takes an important part of the growth chemistry, and the novel superhard was made from the CNOB system. Degree of crystallinity and the bonding nature was manipulated by simply modifying the sample stage design and introducing the external bias. And superhard novel boron nitride, boron carbide, and boron carbonitride was synthesized by the lower temperature plasma model, which was the ultimate goal of this study. Here is the reference I have used for this study. And I would like to acknowledge my postdoctoral mentor, Dr. Yogesh Bohra, and my PhD mentor, Dr. Shane Aaron Catlett. And I also like to thank my dissertation committee member, Dr. Kamata, Dr. Cheng Chen Chen, Dr. Ning, and Gregory Thompson for their valuable insight. And I also like to acknowledge the NSF Explore, FTTT, and our lab members. And I also like to acknowledge Jerry Sewell from the Physics Machine Show, because when I have some idea to make some sample stage, he always helped me to machine it and make the same configuration of the sample stage design. And I also like to acknowledge the UB Department of Physics, and I also like to acknowledge for the funding support from the FTPP and the CPU12, and also I was partially supported by Alabama Export GRSP, so I also like to acknowledge the Alabama Export. Thank you for your attention.